So now I'm going to talk about chemical kinetic mechanisms for the rest of the week. Okay, and so there's lots of experimental studies, and we rely on validating our models against the experimental data. Okay, that's really the point of that slide. Okay, and so and at the heart of everything, though, that I do is the chemical kinetic modeling. Okay, so we use the experimental results, and we develop the model to simulate it using quantum chemistry calculations and then kinetic calculations from those quantum chemistry calculations, okay, to inform the model. But also then the model is informed by the experimental results with which we're trying to validate it, or to which we're trying to simulate. Okay, so chemical model, and who was talking about one-step mechanism, Professor Law, wasn't it, on Monday, and he was saying, oh, we had one-step mechanism, fuel plus O2 gives CO2 plus water plus energy. Okay, and that's why we burn fuels, because we want to get the energy, right? But so for a small hydrocarbon fuel, like methane, actually it involves about 30 chemical species and about 200 reactions to describe its oxidation. So it's not simple, okay? And we have a chemical kinetic mechanism which involves the kinetics and thermodynamics, and also then transport properties if we want to do flame simulations. Okay, and people ask me what I do, and I often say what we do is you picture a fuel like a giant jigsaw puzzle, right? And that what we're trying to figure out is how does it break apart, okay? Does a small piece of the jigsaw puzzle, what am I after doing? Does a small piece of the puzzle break off and that piece goes back and takes another piece? Does O2 go in and take a hydrogen atom? Does the fuel break in half, then in quarters, then further break down, or how does it break down? Okay, and so so that's what we do. And then typically then for any hydrocarbon, the mechanism is built in a hierarchical way. So a hydrocarbon is what it says on the tin. It's a molecule that has hydrogen and carbons in it, okay? And oftentimes now we're looking at oxygenated hydrocarbons, and now we've moved to ammonia, which I'll be talking about on Friday. But it was actually Charlie and Charlie Westbrook and Fred Dreyer that published this hierarchical structure diagram back in 1984 in a paper, Progress in Energy and Combustion Science, which described this hierarchy of chemical kinetic mechanisms. So you've got a hydrogen-oxygen mechanism on top of which we built a CO. Then we have formaldehyde, methanol, methane, and then once we have methane, we go to C2 species, ethane, ethylene, and acetylene, and then ethanol, and then we have C3 species, and so on up. Okay, so we have this hierarchy structure, and this is actually the diagram that they showed. I've taken it directly from the paper. Okay, and here's a nicer one from Bill Pitts. So if we look at hydrogen typically a mechanism involves 8 species and 20 reactions, right? And as we go higher, then the number of reactions increases and the number of species. So methane, as I said, 30 species, 200 reactions, okay? If we go to C3, about 100 species, 400 reactions, okay? So the bigger molecule we go, the larger is the mechanism. And I like this slide, that's why I keep it. It's like a Russian doll model. You start with hydrogen, you go all the way up. You can go hydrogen, CO, methane, ethane, all the way up to C16. You're building and building and building, and it's unending. Okay, so I'm not trying to promote this. I'm just trying to. This is the paper, a paper on hydrogen and CO, which is we call syngas. Okay, and we published this work for hydrogen and syngas back in 2013. Overall, the hydrogen mechanism can be written in one step as H2 plus a half O2, giving H2O. But the actual mechanism that was published in that paper has 20, but it's actually a bit more because some of these are duplicates and so on, and it's quite complicated. But you can see we have the low pressure limit, we have low pressure limit here, we have third body efficiencies, and we have Troy fall off and so on included in this mechanism. Okay, but it comprises here 20 reactions for syngas, and here's the one, CO plus O gives CO2. Maybe there's more. Okay, so this is another sort of famous diagram, and it was published by Jürgen Warnatz in 1981, where he showed actually that there's competition between oxidation and pyrolysis, right? And it was the first time that this was shown. So if we have methane, we can get methyl. And this is a crossroads. So there's kind of two major arrows here. It can oxidize to give formaldehyde, or it can methyl radical can self-react to give ethane. And then ethane can give ethyl, which can give acetylene. And actually, there's a nicer one by Elizello Ranzi here. It's a much more modern version. So here we have methane undergoes H atom abstraction, you get methyl radical, and then that oxidizes at low temperature to methyl peroxy, but at high temperature to almost directly to methoxy and OH, and then methoxy becomes formaldehyde, which gives you formyl, which gives you CO, and gets oxidized to CO2. Actually, one of the most exothermic reactions in combustion is this one, CO plus OH, giving you CO2 plus H. Okay, and it's a very important reaction. Okay, but you also have a pyrolysis mechanism. So methyl recombines with itself to give ethane. You get ethyl, ethylene, acetylene, and then you get aromatic and soot chemistry through the Hacken mechanism that was described by Hai Wang and Michael Frenklock. All right. Okay, and then to these mechanisms you can add other emissions chemistry like NOx and so on. Okay, so there's two arrows here though. So you've got a competition between the reaction of methyl with O2 and HO2 undergoing oxidation, or its self-reaction, self-recombination to give ethane. And the ratio of those reactions decides predicted reactivities, predicted species profiles, and so on in chemical kinetic mechanisms. So it's very important that that competition is properly predicted by a model, okay, or you won't get the reactivities right. Okay, so this is just to give you an idea of a reaction mechanism. Okay, it involves many hundreds and thousands, and we have a mechanism now, C3mech version 4.0. I think there's 22,000 reactions in it and 6,000 species. So they can get as big as you want. Okay, how big do you want it? We'll give it to you, right? But but there's lots of species validated in that, and but here's just a snippet of a mechanism for ethanol. Okay, and I'm just so what we describe in the mechanism then is a series of elementary reactions. That's the point of this. Okay. And it's complicated. So we have 4 actually unimolecular decomposition reactions with different rate constants associated with that. And typically, we can either put the rate constant in either the forward or reverse direction, and it can calculate the reverse from the thermochemistry, or we can provide the rate constant in both directions, and then it won't depend on the thermochemistry that you provide. You still have to provide a thermochemistry parameter, but it won't use it. Okay? If you provide all of the reactions with forward and reverse rate constants in there. Okay? So you've got then hydrogen atoms abstraction from the fuel. There's 3 different radicals that can form, and most of these are showing 3. Actually, for O2, we don't include one of them. I'm not going to go into that. It's just missing here, just accept it's missing. It doesn't really matter. But the idea is that we typically have unimolecular decomposition of the fuel. We H atom abstraction from the fuel by O2, OH, H, HO2, methyl, methoxy, O atom, and so on. Okay? But this is just showing you how, I was using it as an example of how we start to put a mechanism together. Okay? And then once we have all of the fuel molecules and the radicals accounted for, then we build that, we put that on top of our hydrogen CO C1 chemistry. Okay? If that makes sense. All right. Okay, so where do we get the rate constants from? So there's a very large number of reactions, as I said. In our latest one, we have 22,000 reactions. So where do we get those 22,000 rate constants from? Okay, so if there's a direct experimental determination, then we take that, okay? Or from quantum chemistry calculations, more and more, right? We take those. But if they don't, we actually have to estimate them, okay? Based on some knowledge, okay? And a large part of that I'll be talking about. There are online databases. So we have the NIST Chemical Kinetic Database. It's available, it's being discontinued. There were reviews by Bouch, Zhang, and others available. And then there's lots of online mechanisms, ones from GRIMEC, Livermore, Leeds, Connoff, Galway, Polimi, JetSurf, UCSD, KAUST, lots of different ones, okay? I'm promoting this more, and actually I should have updated the link, but this is broken, but I'll update this. This should be c3.nui Galway. Anyway, I'll update this link and you can have that, okay? But the reason I'm saying this is because this website where you can see lots of different groups from around the world that do chemical kinetic modeling. They're all listed in one place. And then you can click there and access the websites of the different groups. So it is actually a handy website. It wasn't me that did this. It was my previous supervisor, John Simi, that set that up. But I think it's a nice website to just get access to other ones. Okay. This is just a simulation based on a mechanism that John Bugler, I spoke about him before, we published in 2016 on the pentane isomers. And this is on N-pentane. Okay. And it's just predicting the ignition delay time as a function of inverse temperature at 5.5, 1, and 2, okay, at 20 atmospheres, okay? Okay, let me go back. One thing I would like you to learn or to understand is, or what do you see? Maybe, can you tell me what do you see here? And I just get you to start. Maybe I shouldn't move too much. Okay. What are some features about this that kind of stand out, or you want to? Yeah.
The two local maxima, like the peak and then the trough.
Okay. There's a peak. Sorry. There's a trough here, a peak here. Yeah. Mm-hmm. Okay. Yeah. Okay. That's one thing. One feature. Yeah.
And cross. Like the lines cross.
The cross, that's interesting, right? Yeah, anything else?
The far end, they're approximately all the same value, all the way on the right.
All the way here, yeah. And then they're all about the same here as well, but yes, that's interesting, right? Anything else?
Yeah, following the same phenomena or trace, there's a difference in values.
Okay, so they all have the same kind of curvature and so on. It's just they're at different extreme, or yeah, that's it. And I think that they're the main features, right? So I'll point them out then, and you pick them up, right? But I think it's good to think about it, and then to try and hopefully you'll be black belts by Friday evening, and you'll understand everything there is to know about why it is that this is the way it is, right? So, yeah, the reactivity reaches a kind of converges here at low temperature, right? And then we see actually lean mixtures are slower to ignite, up to about 1250 Kelvin, right? Stoichiometric mixtures are intermediate, and then rich mixtures are faster to ignite up to 1200 Kelvin or 1250, right? And then once you reach 1200, 1250 Kelvin, lean mixtures are faster to ignite, then stoichiometric, and rich mixtures are slowest to ignite, right? So that's weird, okay? Or it's different behavior. So there must be different chemistry happening in this regime compared to this regime, right? There's different controlling chemistry happening, right? And so, okay. And then, of course, then we have this weird, so there's a, if we draw a line here, across here, there's the reactivity reaches a maximum, and then above the temperature, depending on which equivalence ratio you're at, the reactivity decreases when you increase the temperature. And then it increases again once it reaches this threshold at about 1000 Kelvin. Okay, so that's interesting, right? So here is a general reaction scheme for chemical kinetic modeling. And when I was drawing this, I used the color to try and indicate the temperature that you're at. So blue is cold, like the tap, red is hot, and then brown is kind of intermediate. Okay, that's the idea, all right? So we have RH represents the fuel, and at high temperature, it can undergo unimolecular decomposition, right? Or it can undergo abstraction mostly by these species, right? Maybe I should have O2 over here, but I've listed them color-codedly, right? So that at low temperature, it's OH. At intermediate temperature, the important ones are HO2 and CH3O2, and OH, actually. And then at high temperature, it's O2H, CH3O, and O, and OH, right? So they're all important, right? But anyway, at low temperature, the fuel undergoes H atom abstraction by OH. We get an alkyl radical that adds to molecular oxygen. We get an alkyl peroxy radical. It can isomerize to a hydroperoxy alkyl radical. Add to O2 again to give a hydroperoxy alkyl radical. And then it can give this radical species, which decomposes very quickly to a carbonyl hydroperoxide and an OH radical, okay? So all the way along from here, all the way to here, we have propagation, right? In each step, we're forming one radical. It's only in the last step that from here, so we have the stable carbonyl hydroperoxide that cleaves the hydroperoxide OO bond and giving you a carbonyl alkoxy radical and OH, okay? And this final step, well, these two together give you 1, 2, 3 reactive radicals from one fuel radical, right? And that gives you chain branching at low temperature, okay? So at low temperature, the chemistry proceeds through this channel here, right? So if we are fuel rich, will we have more or fewer alkyl radicals coming from the fuel? Why?
You have more fuel.
Yeah. So the more fuel you have, the more R you'll have. If you have high concentration of RH, you're going to have a high concentration of R, right? So the rate limiting is R, right? And so will rich mixtures be faster at low temperatures if the chemistry is proceeding through this route here? And the answer is yes, okay? So that explains immediately, if I go back, why rich mixtures are faster than lean mixtures at low temperature, right? The richer you are, the more RH you have, the more R you have, the more branching you're going to have, okay? So that gives one answer straight away, okay? Right. At intermediate, okay, so that's probably good enough for now. Okay. I'm going to talk about low temperature chemistry tomorrow and Friday, not today, okay? So we're going to park that, right? And today, we're going to talk about high temperature kinetics, okay? So we're going to go we're going to be talking about after the crossover, or when the crossover happens, from about 1250 and higher in temperature. And we're going to talk about the kinetics in that regime, okay? And the important kinetics, if I go back, so if we look at conversion and at high temperature, what we see is we get very little fuel conversion, and then we get a strong fuel conversion at higher temperature. Okay, why? Okay, because what happens at high temperature is we need there's a high activation energy barrier to break the CC bond or the CH bond to form the two radicals that need to be formed, right? So to get initiation, the fuel undergoes H atom abstraction actually mostly by O2 at the start, because what are the initiation reactions that we can have? If we have fuel oxidizer, we have fuel and we have O2 in the system. So the two initiation reactions that can occur are unimolecular fuel decomposition or H atom abstraction from the fuel by O2. But H atom abstraction, the activation energy for H atom abstraction from the fuel by O2 has a barrier of about 50 kilocalories per mole. So it's relatively high, okay? H atom is very, very low. O atom is the lowest. It can be almost 0 or maybe 1 kilocalories per mole. So it's very low. But there's no OH there at the start. So we have to generate it, okay? So at high temperature, we have to overcome an energy barrier to get reactivity. So we see here the reactor temperature, there's very low conversion at low temperature because the activation energy barriers are such that we cannot overcome them. And I'll talk a bit more about that in the next couple of days, okay? There's very nice slides that I got from Tiziana Faravelli, which shows this, okay? But what's one of the most important reactions then is after we get the radicals, these radicals decompose, undergo beta scission, and form H atoms and methyl radicals, ultimately, okay? H atoms and methyl radicals. And typically then, at high temperature, the rate-limiting species is not H atom. It's actually O2, okay? So we get a lot of H atom, and the rate of reaction, if we look at this reaction then, H plus O2 gives O plus OH. The rate of this reaction is equal to the rate constant times the concentration of H atom times the concentration of O2. And if we have lots of H atoms, what's limiting us is actually the concentration of O2. So at high temperatures, right, and if you learn nothing for the week, right, I remember Charlie, he picked me up at the airport. I arrived into Livermore, and it was close to what you call it, Independence Day, right? But he said, look, Henry, if I don't know why he said that, but he said, if you learn nothing for the time that you're here, learn that the reaction H plus O2 gives O plus OH. That's the most important reaction in combustion, right? And it is so important, right? And so if we go back then, I go back one, okay. We see if we're at high temperature, right? Lean mixtures are faster than stoichiometric or faster than rich. Why? Because in lean mixtures, we have a higher concentration of O2, right? And if H plus O2 is controlling everything, and we have lots of H, and the rate controlling species is O2, the higher the concentration of O2, the faster is the rate of reaction, right? And it's in a nutshell for high temperature kinetics, right? That reaction dominates so much, right? So, but this is actually very nice. It was actually, I think, Professor Miyoshi that showed me this, right? So actually the rate controlling step is actually H plus O2 gives O plus OH. But this is a very nice system, and he showed this, right? You have H plus O2 gives O plus OH, but you have, I can't remember where he published it. I didn't see where he published it, but he had it and I borrowed it from him. But it was Professor Miyoshi in Japan that I got this idea from. But the O atom that you form in this reaction then reacts with a molecule of H2 to give H plus OH. And then the OH that's formed in both, that's available, reacts with O2 to give water plus H, right? So actually, if we go through it and we look at the net effect, okay, we have H used here, but it's generated here. We have O generated here, but it's used here. We have OH generated here, but it's used here. The net effect is we have 2H2 plus O2 gives us H plus OH plus water, right? So we have, the net effect is we have two stable molecules, the reactants, hydrogen and oxygen, reacting to form two radical species, H and OH, with the liberation of water, which when water is liberated, you get, it's exothermic, okay? So not only are you getting radical species produced, but you're also getting heat released, right? And so the whole process, and what the limiting step is this H plus O2 gives O plus OH. That's the trigger, right? So when that happens, you have this net effect, okay? It's pretty cool, okay? That's with hydrogen in the system, okay? So if we look at high temperatures and we do sensitivity analysis, I just take some from what I published years ago. This is one for that Stephen Dooley, he actually worked here at Princeton for a good few years with Professor Dreyer. He's in Trinity College Dublin now in Ireland. But he worked with me, he did his PhD, and we looked at the time, methyl butanoate. But this plot could be true for nearly any fuel at this condition, right? And what I mean by this condition, I mean like 1% fuel, phi is equal to 1 in argon at a pressure of 1 atmosphere. So if we're at low pressure and high temperature, we're in the high temperature kinetics condition. And if you're in that high temperature kinetics condition, you're going to see a sensitivity analysis for any fuel that will look like this, right? So we see, not surprisingly, I just went on about it, H plus O2 gives O plus OH. Huge sensitivity, big bars, right? At both 1300 and 1600 Kelvin, right? And so if the bar is to the left of the center line here, we're enhancing reactivity. If it's to the right, it's inhibiting reactivity. Okay, the next most important reaction enhancing reactivity is methyl butanoate decomposition. Okay, unimolecular decomposition of the fuel. Okay, but if I scroll down then, now we start to see C1 chemistry, C2 chemistry, C2 chemistry, C1 chemistry, C1 chemistry, hydrogen chemistry, C1 chemistry, hydrogen chemistry, hydrogen chemistry, C1, C2 chemistry, methyl butanoate, and then C1 chemistry, right? So an awful lot of the reactions here are involving the hydrogen, the C0, C1 chemistry set, okay? And they're very important to methyl butanoate oxidation. But you'd see them for every hydrocarbon fuel or every oxygenated hydrocarbon fuel. You're going to see the same reactions showing up again and again, right? Okay, and they're just highlighted there. So yellow means hydrogen, orange means C1, C2, and then the blanks are the actual fuel molecule itself. So there's not a lot of fuel ones. You have fuel decomposition, H atom abstraction from the fuel by methyl, by OH. One thing, and here's another thing to bring home with you that I want to highlight. Okay. And it's not quite true. There's a lot of them here. This is unusual, and I don't want to go into it here. So we have methyl butanoate plus methyl. That is actually enhances reactivity. Methyl butanoate producing MB4J, that enhances reactivity. But methyl butanoate plus any radical producing MBMJ and MB3J, I don't know what they are, right? But they're different radicals from the fuel, right? So if you produce one fuel radical, right, it enhances reactivity. But if you produce the other ones, they inhibit reactivity, okay? So there's a branching competition going on. So some radicals produced from the fuel will enhance reactivity for you. The other ones will inhibit it, right? Okay. But one thing that we see, methylbutanoate plus H giving any radical, right? And any fuel plus H giving any radical always inhibits reactivity. Why? And you see here, look, it's the second most inhibiting reaction on the graph. Why would that be?
Consuming hydrogen radical?
Spot on, right? So why? Because it consumes H atom. What does H atom like to do? It likes to react with its buddy O2 to give O plus OH. If it does that, we have a huge enhancing effect of that. So always, fuel reacting with H always inhibits because it's competing with O2 for hydrogen atoms. Exactly right. Okay? And you'll always see that. And it's sort of counterintuitive because you're abstracting a hydrogen atom from the fuel and you're generating radicals. And you would expect that should always give you an enhancing effect. Okay? But because of the importance of this reaction, it always inhibits. Okay? So that's just something to remember. Here's another one. So here's sensitivity. Sorry, this was sensitivity, I should have said, to ignition delay time. Okay? Here's sensitivity to flame speed, right? And this is just a plot that I took from Eliseo Randi and Professor Law from Progress in Energy Combustion Science in 2012, right? And again, you can see here, look, yellow are hydrogen-oxygen chemistry, hydrogen-oxygen chemistry. Orange, C1, C2 chemistry, okay? The only reaction that has any sensitivity that's higher is just this propene plus H giving this allyl plus H2, right? That's the only reaction beyond the hydrogen-oxygen C1, C2 chemistry that's showing any sensitivity, okay? And this is for methane, ethane, propane, N-butane, and isobutane flame speed. There is no isobutane, N-butane, propane parent mechanism reactions showing up for the flame speed. Okay. So another thing to remember in flames is that H atom chemistry is hugely important. Why?
I think because that's the main flame propagation reactions.
Yeah, but why in flames? Like hydrogen atoms are produced in shock tubes. They're produced in rapid compression machines. But we don't see such domineering effect of H atom as we do in flames. So sorry, I should have pointed out, look, H plus O2. That one isn't, but HCO, H, not H, right? H is nearly in every one of those reactions, H atom. Okay, and I'm making an impression on it, on asking, because it's really important. I want to highlight it, because H atom can diffuse, right? So its transport properties are very important for flames, and it's the one species that you need to have good transport properties for when you're doing chemical kinetic modeling, right? It's the most important species in a flame, right? And so in flames, what happens is H can be produced in the reaction zone way out, but can diffuse back to the reactants, and then and its chemistry then is very, very important. Okay, so you'll see in any sensitivity analysis you do to flame speed or flame simulations, you'll see the H atom chemistry just comes out the whole time as dominating. Okay, and this bar will always be top of the pops. Okay, for in a flame. Okay, so what am I saying? In small, okay, I won't. So for chemical kinetic modeling then, the one thing you need to have is a very good small species chemistry model, right? Because at high temperature and low pressure for all species, or for ignition delay times, and for flames and flame speed predictions, that chemistry is controlling the reactivity, right? And so if you don't have an accurate small species chemistry, you're not going to have good predictions of the model, okay? So in small molecule kinetics, each elementary reaction is treated individually. And typically, many of the elementary reactions are rather idiosyncratic or unusual. They have a temperature curvature. Sometimes we have to put in, and I'll show you in a second, duplicates to describe the Ray constant, and so on. So you need extensive validation experiments, though usually do exist, because for these small molecules, they're small enough that we can actually do experiments with, and they're volatile enough that we can look at them in the gas phase, and they're easy to deal with, okay? So the principal reactions are usually H plus O2 gives O plus OH, and then by extension, because it competes with that, H plus O2 plus M giving HO2 plus M, right? And then CO plus OH giving you CO2 plus H, okay? Because once you produce the OH abstracts a hydrogen atom and you get water, okay? So this is going to go, the OH that's produced here, the O atom that's produced here will abstract to give you OH, will then go on to give you water, okay? So ultimately, these are going to give you water and CO2 and be the exothermic reactions in combustion. So hence their importance. Okay. Okay, so I made it my business when as I said to you on Monday, when I went back to Galway, having left Livermore and published the N-heptane and isooctane mechanisms, to make sure that I had a very good core species chemistry mechanism for the reasons that I just said, right? And so we published a Ramco mech, maybe about 10 years ago now, more, okay, describing small species chemistry, including C1, C2 species, and taking, as far as possible, measured Ray constants. And if they haven't been measured experimentally, those calculated from ab initio calculations, and then putting that into the mechanism. And then try to validate the mechanism over a wide range of conditions, all right? So that was what we do. And this is just showing then a synopsis of the species that we simulated, the data that we had available, shock tube, jet stirred reactor, flow reactor. So these would be species profiles. These are flame speeds and flame speciation data, and then these would be ignition delay time data for over a wide range of temperature, pressure, and equivalence ratio. Okay, so let me start. Okay, as I said, there's three distinct regimes, and I shouldn't go into this in great detail. Okay, well, I have to actually. So let me, okay. We have, at high temperature, we have this set, which I just spoke about a little bit earlier. At intermediate temperatures, there's slightly different chemistry that is controlling. Okay, we have H plus O2 plus M giving us HO2 plus M. That does give us some HO2 at intermediate temperatures, but we don't get a lot of H atom because we don't get a lot of beta fission until towards the end of the intermediate temperature regime, okay, the higher end, okay. We do, though, get a lot of HO2 through the fuel. First of all, undergoing H atom abstraction. So we get RH plus O2 to give HO2, right? And then we get fuel plus HO2 gives you the radical plus H2O2, okay? And then H2O2 that's produced from HO2 gives you two OH radicals. And at intermediate temperatures, this is really the dominant controlling reaction, right? So at intermediate temperatures, it's HO2 radical producing H2O2, which then produces lots of OH radicals that drives the reactivity, right? Where's HO2 coming from? Largely, actually, a large proportion of it, and I'll show you this tomorrow. You have fuel radical adds to O2 to give RO2, and that RO2, the alkyl peroxy radical, then gives you an olefin plus HO2. Okay? So at intermediate temperatures, this is still switched on, and I'll prove that, or I'll demonstrate that a little later when I have it available. And then, of course, at low temperature, we get an alkyl radical, it adds to O2, we get RO2. That RO2 can isomerize to QOH, can add to O2 again, and then we get the peroxy hydroperoxy alkyl radical, and then that decomposes and gives you a carbonyl alkoxy radical and 2 OH radicals, and we get chain branching at low temperature. Okay, so we have the high, intermediate, and low temperature chemistry. Okay, synopsized there. Okay, this is a very important feature to talk about in hydrogen oxidation. Professor Law was talking with me about this, and he actually published a paper on this relatively recently. It's only 7 years ago. Okay, but this is a problem that has been, well, not known, but been studied, and a large part of it is known for a long time, 30, 40, 50 years or more, right? So, but the idea is this: if we look at hydrogen oxidation in a closed vessel, right, and we can have different reactions that can occur, okay? So we can have initiation. So we have oxygen abstracts a hydrogen atom from hydrogen, you get HO2 plus H, okay? You can have then H2 undergoes H atom abstraction by HO2 to give water and OH, okay? We have H2 plus OH giving water plus H. Okay, we have H plus O2 plus M giving HO2 plus M in a propagation, and we have H plus O2 giving O plus OH giving branching. Okay, so all of these reactions can occur. Okay, and in addition to that, we can have H atom diffusing to the wall in a termination. Okay, so let's just look at this diagram then. I come over here, and I have 800 Kelvin kind of highlighted there. So let's just look at the condition at 800 Kelvin. Okay, so if we're at very low pressure and a temperature of 800 Kelvin, at very low pressures until we get, and this is in pascals, so forgive me, I don't know what this is, but let's just say it's about 3 times 10 to the 2 pascals, right? And lower, right? We have no steady reaction or no explosion. So what's happening in this regime here? What happens is that we're at such low pressure that the H atom that's produced in this sequence of reactions diffuses to the wall, right? And it doesn't meet the other species. It doesn't meet O2 to react, or at least not enough of it meets O2 to give us the chain branching that's needed to get explosion. Okay? So preferentially, it diffuses to the wall. Not all of it, of course. You get some reaction. But because you're at such low pressure, and then in regime 1 to 2, you have now sufficient concentration, essentially, and of the species, sufficient density in the system, that H reacts with O2 to give O plus OH in the chain branching reaction, and you get explosion. Okay? So you get that branching, and you get explosion. And that occurs up to, we say, a pressure of, what is it, about 7 times 10 to the 3 pascals, or 8 times 10 to the 3 pascals at 800 Kelvin. Okay? And then at pressures above that, again, up to, we'll say, 8 times 10 to the 5 pascals, we have steady reaction again. We don't have explosion. Why? Because now the concentration of M is big enough that the rate of this reaction, remember, the rate of this reaction is going to be equal to the rate constant of this reaction times the concentration of H atom times the concentration of O2 times the concentration of M. Okay? And now the concentration of M is big enough that it's able, that rate competes with the main chain branching reaction, H plus O2 gives O plus OH. And so we don't get explosion anymore. We get steady reaction. Okay? And then beyond this limit was really the focus of the work that Professor Law did in this paper from PCCP in 2018. And there they showed that actually it's the formation of HO2. And then you have HO2 abstracts a hydrogen atom from the fuel to give H2O2. This is wrong. I don't know why I have it written like that. This should be H2O2 plus H. Okay? I don't know. I was looking at that. I better correct that straight away because it's bugging me. I don't know where that came from. Okay. Okay, so you get H2O2 plus H, and then that H2O2 decomposes to two OH radicals. And when that happens, you get explosion again. Okay? So you're not at high enough temperature and concentration of H2O2 to get it to decompose until you get high enough in pressure. And now the concentration of H2O2 becomes high enough, you get enough OH radicals that you then get explosion again. Okay? Does that make sense to everybody? So and this is a very famous explosion limit diagram for hydrogen oxidation. Okay? It's very well known. Okay? And this is just another explanation of what I've just said. So I'm not going to say it again. Okay? This is a graph that I took from the paper, that hydrogen syngas paper that I talked about earlier. And this is just showing, it's simulated ignition delay times using a mechanism from Fred Dreyer, published in 2004. Okay? And we're simulating ignition delay times from 900 Kelvin to 2000. And what we see, we have three different pressures tested here. We have 8, 16, and 32 bar, right? And what we see is that at low temperature conditions, the higher pressure is faster than the intermediate temperature, and the lowest pressure is slowest to react. Why? Because at low temperature, H plus O2 plus M gives HO2 plus M. That's sort of linear happening. And then the HO2 that's produced abstracts a hydrogen atom from the fuel to give H atom and H2O2. And then H atom and H2O2, that concentration will be higher at 32 bar than it will be at 16 bar than it is at 8 bar. And hence, the higher in pressure you are, the higher in concentration you will be for HO2 and H atoms and H2O2. And therefore, the system will be faster. Okay? So that's at low temperature. However, when you come into this regime, you can see now that the 8 bar becomes faster than the 16 bar, which is intermediate. And actually, the 32 bar is actually slowest. Right? Why? Because now the H in this regime, the competition of this reaction, H plus O2 plus M with HO2 plus M, is in competition with the H plus O2 giving O plus OH, right? And as we go higher in M, the more HO2 is formed, and the less we get O plus OH, right? So in this regime, at this temperature, and at all the pressures, it can compete with H plus O2 gives O plus OH, right? And what's happening in here is that at 8 bar then, we have a lower concentration of M, a lower rate of competition going to propagation, and hence H plus O2 gives O plus OH is dominating still, and the 8-bar experiments are faster than the 16, which are faster than the 32. Okay, and then beyond, I don't know what this is, 1350 Kelvin or so, then it becomes again linear. 32 bar is faster than 16 bars, faster than 8 bar, because there's no longer competition. It's all dominated by H plus O2 gives O plus OH. And the higher the pressure you are, the higher the concentration of both H and O2. Okay, and hence the reactivity is faster. Okay, so I hope that you understand that plot. Okay, so chain branching at high temperatures, the reaction H plus O2 plus O gives O plus OH dominates. H atoms come from the decomposition of formal radical, vinyl, ethyl, isopropyl, and so on. Okay, and this sequence of reaction requires high temperature, and hence these are important at high temperatures. Sorry, because they have activation energy barriers that are relatively high. Okay, and here's a very interesting graph or plot, and it's data published by Alex Burkhardt back in 1971. Okay, again here we have inverse temperature and log of ignition delay time. So it shows clearly here that methane is slowest to ignite. Then propane, butane, pentane are about the same, but propane is slower, then butane is a bit faster, then pentane is a bit faster. But actually, ethane is much faster, right? So actually, methane is slowest, ethane is fastest, and then C3, C4, C5 are in between, right? So that's kind of weird. One thing to note then, well, let's look at our O2 concentration. And let's just see, well, are the O2 concentrations changing from methane to ethane? Because I said if O2 is dominating, right? And so if the O2 concentration changes, then H plus O2 gives O plus OH. That's going to be controlled, right? But actually, here's methane is 15.4%, here it's 16.1, here's 16.25, here's 16.3, and here's 15.91. Actually, in all cases, the O2 is about the same, right? So what is changing here is actually the H atom concentration, okay, among these fuels, right? And you see that, why am I going there? Okay, we have H plus O2 is dominating. We're getting lots of H atoms. But in the case, sorry, let me go back. I should explain this a little bit more. In the case of methane, what radical are you going to get from methane? It undergoes H atom abstraction. What are you going to get? Methyl radical. No H atom. Okay, so are we going to get much H plus O2 gives O plus H? No, because it doesn't exist, right? It's the slowest. What about ethane? I just gave the game away. Okay, ethane, it undergoes H atom abstraction. We get ethyl radical, right? What's ethyl radical going to do? It's going to undergo beta scission to give us ethylene plus H. Okay, so that's going to give us lots of H. Okay, and it'll give us one radical, ethyl, and that one radical will give us all H atoms, right? And that dominates. Okay, what about propane, butane, and pentane? What about those guys, right? So we'll say, sorry, I'll write here. So methane gives methyl, no H, okay? And then we have ethane, C2H6, gives C2H5, and that gives C plus H, and only H, right? But what about in the middle? So what about C3H8? So if I'm going to draw it like this. Forgive me, I'm not going to put the H's if you don't mind. I don't have much time, right? But we can get two radicals. We can get N-propyl or we can get isopropyl, right? If we get N-propyl, we're going to get ethylene plus methyl. And if we get isopropyl, we're going to get propene plus H, right? If you look at the other ones, C, 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 that will give you two radicals, that one and that one, okay? And then this is going to give you ethylene plus C2H5, which will give you another ethylene plus H. But this one is going to give you, sorry. Can everybody see what I've drawn there? Is it behind the, sorry. Okay. So, and it's pretty cool. And it's very simple, right? So, for methane only produces methyl radicals. Okay, so that's slowest to ignite because there's no H atom. And then ethane only produces ethyl radicals. And ethyl radicals undergo a beta decision to give ethylene plus H. So it only produces H atoms. So that's fastest to ignite because we have H plus O2 gives O plus OH. And then in between that, we have propane, butane, and pentane. But if we look at the decomposition of propane, propane can undergo H atom abstraction producing N-propyl and isopropyl radicals. N-propyl radicals will then bear decision to give ethylene plus methyl, not a H atom, or propene plus H atom. So it gives you a mixture of methyl and H, right? As does butane. Butane produces 1-butyl and 2-butyl radicals. 1-butyl radicals will produce 2 molecules of ethylene and a H atom. That'll give us high reactivity. But 2-butyl will give us propene and methyl. Again, not H. So fastest to ignite will be ethane. Slowest to because it produces only H atoms. Slowest to ignite will be methane because it produces methyl radicals, no H atoms. And then the other species will have reactivities which lie in between both because they produce both H and methyl radicals, a mixture, right? So methane is going to be slowest. Ethane is going to be fastest, and all the other guys are going to be in between, right? Because you're getting methyl and H, and that's exactly what you see. And it's as simple as this, right? Because you have H plus O2 giving you O plus OH dominating. Okay, that's really cool, right? Okay, so I'm going on about that again, but it's so important, and I keep repeating it. Okay, so this is probably a good time for us to take a break. Let's come back at 22, if you don't mind, and then I'll go through the mechanism from there.